Let's understand bending moment diagram. A simply supported beam with span L, supported at A and B. Now apply a uniformly distributed load, 12 kilonewtons per meter, across the entire span. Because the loading is symmetrical, the two supports share the load equally. Raw equals RB equals WL2. The shear force starts positive at the left support, decreases linearly under the UDL, reaches 0 at midspan, and becomes negative toward the right support. Mmax equals WL squared 8. Now look at the bending moment. It is 0 at both supports and reaches its maximum at midspan. So remember, maximum shear occurs at the supports, while maximum bending moment occurs at midspan. Let's understand shear force diagram. Why is the shear force usually highest at the supports of a simply supported beam? Imagine a beam carrying a uniformly distributed load, or UDL, across its entire span. The supports push upward to resist this load. For a symmetrical UDL, each support carries half of the total load. RA equals RB equals WL2. Starting from the left support, the shear force is at its maximum positive value. As we move along the beam, the UDL continuously reduces the shear. At the center of the beam, the shear force becomes 0. Moving toward the right support, the shear becomes negative, reaching its maximum magnitude at the support. So remember, under a full span UDL, shear is maximum at the supports and 0 at midspan. How to calculate beam reaction? Let's understand with an example. Take a simply supported beam with a 4-meter span and a 10 kN point load right at the center. To find the reactions, we use the basic rules of static equilibrium. Take moments about support A. RB times 4 minus 10 times 2 equals 0. So the reaction at B is RB equals 5 kN. Now use vertical equilibrium. Raw RB minus 10 equals 0. So RA equals 5 kN. Therefore, each support carries 5 kilonewtons. RA equals 5 kN. RB equals 5 kN. That's the first step before we can draw the shear force and bending moment diagrams.